Well, thank you all very much. Can everyone hear me? Yes. Great. Thank you very much. Thank you, Janet. Thank you, Susan. Thank you all for coming. Thank you to the National Academy of Sciences. It's a great honor to be here, though I was a little disturbed to find out that the attitude of the program is, what's the worst that can happen? We're about to find out. And thank you all for coming out on a Wednesday to hear about physics and superheroes. I hope to entertain you, and if I can't do that, at least educate you. As mentioned, I'm a professor at the University of Minnesota in the School of Physics and Astronomy. So let me begin with a little background. How did a mild-mannered physics professor become associated with Spider-Man and Superman? As mentioned in the introduction, in my day job, I'm a condensed matter experimentalist, so that means I work in a laboratory rather than doing theory. Condensed matter is a fancy way for saying solid-state physics. I've done work on amorphous silicon, as a material in solar cells and in flat panel displays. I've been studying electronic noise in these materials, which is very interesting. For about 10 years, I did studies on granular media, or sand piles. Sand was very hot in physics there for a while. And most recently, I have a collaborative project with professors in neuroscience, applying techniques we developed to study noise in disordered semiconductors and applying them to the brain. But that's not why I'm here tonight. I'm here because of this freshman seminar class that I created. And really I'm here because on May 2nd, 2002, I published an op-ed in the Minneapolis Star-Tribune where I pointed out that a key element in a Spider-Man story is a textbook illustration of forces in motion. I thought, well, Spider-Man's going to be on the big screen in the movie theaters. This is a good opportunity to get some physics in the newspaper. The University of Minnesota, and so they published this. I'll talk about the story actually a little bit later on tonight. The University of Minnesota put out a press release saying, well, Spider-Man's in the movie theaters, but if you want to know about the science of superheroes, the person to ask is Professor Jim Kakalios, teaches his freshman seminar, blah, blah, blah. Now, the university has put out press releases about me before, about my work on 1 over F noise and amorphous semiconductors. Result? 0. You write one story about Spider-Man, however, and there wound up, by Monday, the article came out on Friday, Spider-Man opened on Friday. By Monday, there were calls from CNN, BBC, the London Times. The Associated Press came to my office, where I just happened to have these lecture demonstration tools. At this stage of my life, I've reconciled myself to the fact that I could win 3 Nobel Prizes, and I know what photo they're using in my obituary. I say this to my colleagues. They say, win 3 Nobel Prizes, like how? On eBay? This was an Associated Press story, so it went around the nation. Actually went even further than that. One of the graduate students brought back a clipping where I think I know what they're saying about me here. And then I started showing up in places that physicists don't usually appear. So if you're ever playing Trivial Pursuit Volume 6 and you get card 291, the science question, the answer is kryptons. The question, what planet's gravity did science professor Jim Kakalios estimate by calculating the force needed to leap over an Earth building in a single bound? I didn't even know about this. One of the graduate students brought this to my attention. I showed it to my department chairman and I said, Alan, who's the most famous scientist you know? He thought for a second and said, Stephen Hawking. Who's not a genius? Oh, well, then it's you. And then again, in journals and magazines that you don't usually see physicists, so if you're ever at like the barbershop or the dentist office, this old issue of People magazine, there's an article about me, and you can read the whole thing closely, and to my friend's disbelief, not once do the words indicted or quiet loner appear anywhere. I have to say that on one level, this article in People has been a bit of a disappointment. here's on the cover, and here's Nicole Kidman, and this is one of her first interviews where after she's broken up with Tom Cruise. And she hasn't fully recognized the exact caliber of the bullet that she's dodged at this point. Yeah, like he's worried about me. And here you see the Oscar winner opens up about her kids, Tom, and her heart. I'm waiting for someone to rock my world. And I'm saying, page 118, page 118. A middle-aged college professor who still reads comic books. Surely this is every woman's dream. And my wife says, oh, way off. But the premise of the class and the book and my talk tonight is that comic books actually get their science more right than you'd think. Here is an example from an old World's Finest story featuring team-ups of Batman and Robin and Superman. And here's Victor Danning, a crook who has become super intelligent through a mechanism that I'll mention in a moment. And he wants to find out where the Batcave is. It's not really explained why he wants this address, but it's just taken as a given that if you're a crook, you want to know where this Batcave is. And his henchmen protest, nobody's ever found the Batcave. And Danning says, nobody with my mental power ever tried. Listen, I want you to bury sticks of dynamite in deep rock outside Gotham City and then set them off. You mean the shock waves from the explosions can show where the Batcave is? Yes, wherever there's a cave, the wave travels at different speeds. And that'll show up like a big cave, like the Batcave, on my radar seismograph. Well, this is right. Sound waves, pressure waves, do travel at different velocities depending on the density of the material. This is, in fact, how geologists search for underground pockets of natural gas or petroleum. In the old westerns, the tracker would put his ear to the railroad track because they could hear the vibrations of the oncoming train much faster through the steel rail than through the air. So here's an example of getting their science right as part of a superhero story. Sometimes how they do science is very wrong. Here's earlier in the story, another scientist, John Carr, giving a presentation at a scientific meeting. He's developed a brain amplifier that could increase any man's mental power 100 times. But there's one ingredient that's still missing, and I haven't found out yet what it is. Now, I have sympathy because I have invented a device that will turn lead into gold and tap water into gasoline. But it's missing one key ingredient. And as soon as I know what it is, I'm off to the races. I like this part here in the next panel. Here's Victor Danning, and he's thinking, if I had that invention and could find the missing ingredient, it could make me super intelligent. Then I'd be able to loot the world. And I tell the students, that's what you need, confidence. I love this part at the top here also. One uninvited guest is present, Victor Danning, crooked ex-scientist. Because it doesn't matter how many advanced degrees you have. Once you're crooked, you're out of the club. We just strip the epaulets off the lab coat and toss you out on the street. Now, my job is not to look at the superpowers and say, this is how they would physically work. The superpowers are physically impossible. Oh, wait, spoiler alert. The superpowers are physically impossible. And I don't see my job as just being Professor Grump going around saying, this could never happen, and this is impossible, and what's the deal with the Hulk's pants anyway? Unstable molecule. So what we do is we grant each character a one-time miracle exemption from the laws of nature. And we say, if you were super strong, or could stretch like a rubber band, or could run at super speed like the Flash here, or Dash from the movie The Incredibles, could you run across the ocean, or up the side of a building? Could you catch bullets in midair, drag people behind you in your wake? All things these characters are shown doing, all things that are correct from a physics point of view once you make that suspension of disbelief. Here's an example. Here's the Flash. He has a superhero who can run at super speed. A crook is shooting at him. Not a problem. The Flash is faster than a speeding bullet. But what about the innocent bystanders in the way? The Flash is not super strong or invulnerable. He's just fast. But with a sweeping motion, the Flash plucked them, the bullets, right out of the air before they could harm him. Editor's note: Flash's action in stopping the bullets is similar to that of a baseball fielder who stops a hot grounder by letting his glove travel momentarily in the same direction as the ball. This is right. This is a physically correct use of the superpowers. If you're going at the speed of the bullet, you can pick it up and it's not a problem. Just this morning, I picked up an object going 600 miles per hour when I poured myself some ginger ale on the airplane. I'm going 600 miles, it's going 600 miles, not a problem. If I'm standing still and it's going 600 miles, then I got a problem. So, this is the type of thing that I'm interested in, these nuggets here. It's not just classical mechanics. You can get some advanced stuff. Here's the Flash again. He's trying to catch someone. The mighty monarch of motion pours it on. They always use these great alliterative things. Monarch of motion, the scarlet speedster, the crimson comet, the tornado titan, the viceroy of velocity. Here we see, it's taken me a little longer than usual to reach light velocity. I wonder if I'm tired or something that could affect my super speed. Good gosh, there's no doubt of it. I'm slowing down. I'm going slower and slower despite all my efforts. I can't go any faster because I'm getting heavier. Something's happening to me. Now, those who know Einstein's special theory of relativity know exactly what's happening to the Flash. An alien is shooting him with a gravity-increasing ray. But if you take it out of context, it's a beautiful illustration of Einstein's theory. So, this sounds like a silly premise, but there's actually something serious that I'm trying to get across here. In my time at the University of Minnesota, it has come to my attention that some of my students actually find physics dull. I know, I felt the same way. This was driven home to me one day when I was coming back after lunch and I saw two students leaving the physics building. It was clear that they had just had an exam returned to them. I'm going to put up here in a moment exactly what I overheard. But in deference to the National Academy, I'll clean it up. The taller student said to his friend, I'm going to bleep and buy low and bleep and sell high. I don't need to know about no bleeping balls thrown off no bleeping cliffs. Now, I contend that there are at least 3 nuggets of wisdom contained in these two sentences. The first, the secret to financial success. So if you learn nothing else tonight, now you got that. 2, the second one, for those who are scholars of English grammar, is the fact that bleeping can be both an adjective and an adverb. Though I suspect some of you already knew that. And that many students don't find their introductory physics classes relevant. This is driven home in the expression you always hear from students, when am I ever going to use this in my real life? Interestingly enough, whenever I use superhero examples, students never wonder when they're going to use this in their real life. Apparently they all have plans after graduation that involve spandex and patrolling the city, and knowing as I do how many crooked ex-scientists there are out there, I have to say that's probably a good thing. But the superheroes are just there as illustrative examples of real physics principles. Once we bring in the real physics, we then show how this applies to everything from how airbags save lives to how cell phones work and how your microwave oven cooks your dinner. So I hope that you this evening are so busy enjoying this superhero ice cream sundae that you don't notice that I'm sneakily getting you to eat your spinach at the same time. So the first thing I want to talk about is that story with Spider-Man that was published in the Minneapolis Star-Tribune, featuring the death of Spider-Man's girlfriend. We're all familiar with the story of Spider-Man, created in 1962 by Stan Lee and Steve Ditko. High school student Peter Parker, bitten by a radioactive spider, doesn't die, but gains amazing powers and abilities which he fights crime as the Amazing Spider-Man. The story I want to talk about was published in Amazing Spider-Man number 121 back in 1973. The Green Goblin, one of Spider-Man's foes, has kidnapped Spider-Man's girlfriend, Gwen Stacy, and brought her to the top of the George Washington Bridge in order to lure Spidey into battle. During the fight, she's knocked off the bridge, where she falls to her apparent doom. Spider-Man shoots his webbing down after her and manages to stop her at the last moment, though those with good eyes will see a little snap sound effect here by her neck that will have bad consequences in a moment. He hauls her back up to the top of the bridge, where he discovers, to his horror, that she is in fact dead, even though he caught her in the webbing. And this was a big deal in comic books, 1973. It was the first time that an innocent bystander and a long-standing recurring character died when the hero and villain faced off. And in 1973, it's been 35 years, and Gwen Stacy is still dead. In the comic books, everyone gets better, but Gwen is in this small select fraternity of characters who've remained dead. And almost immediately a controversy arises as to the cause of the death. Here's the Goblin taunting Spider-Man. "Romantic idiot, she was dead before your webbing reached her. A fall from that height would kill anyone before they struck the ground." Which, if this were true, the implications for bungee jumpers and skydivers would suggest that somebody's not telling us the truth about something. But comic book fans have long argued then, after this, was it the fall that killed Gwen Stacy or was it the webbing? And in 2000, Wizard magazine, a monthly magazine for comic book fans, listed this as one of the great controversies among superhero comic books, at the same level as who's faster, Superman or the Flash? The Flash. Well, to answer this in my class, we turn to physics. We start with a very simple equation. Distance is average speed times time. If you have an average speed of 60 miles an hour and you drive for an hour, you've gone 60 miles. Right. Now here's the problem. She starts with a velocity of 0 and winds up with a large velocity v. What's the average? Well, if I have two students in class, one gets a grade of 0, one gets a grade of 100, the average grade is 50. So I'm going to take just 0 plus v over 2 for the average velocity. The time that we can figure out the time she spends falling is the time at which this speed changes, which is the rate of change, the change in speed over time is the acceleration, which is due to gravity. And we know what this g is, the acceleration due to gravity. And we can rearrange this so that the time she spends falling is the velocity, v minus 0, over g. And that makes sense too. For a given acceleration, the faster you're going, then the longer you've been falling. Right? It's the same way that if you're in a car and you're going 5 miles an hour in a parking lot, you slam on the brakes, you come to rest very quickly. You're going 100 miles an hour, you slam on the brakes, it's going to take you longer to come to rest. So the time should depend on the velocity. We do a little bit of algebra, and we get an expression that relates her velocity to the height that she's falling, the distance, the acceleration due to gravity, and a number 2 that we can look up. Now, let's assume that she's fallen, say, 300 feet. Let's neglect air resistance, which you always do in these physics problems. Well, after 300 feet, if she starts with 0, it turns out that she's going nearly 95 miles per hour. How much force would the webbing have to supply to stop her? We'll use force equals mass times acceleration. Acceleration is change in velocity over time. We'll just bring the time over here. So we have force times time over mass times change in velocity. Mass times velocity is a quantity called momentum. We represent it in physics by the letter P because it stands for momentum. Rocket scientists. Well, this is not the time she spends falling. This is the time at which the web acts to slow her down, to stop her. She's going 95, her change in velocity is 95 miles an hour. Eventually, she's going to stop. Her mass, say, is 50 kilograms, which would mean that she weighs 110 pounds. If the webbing stops her in half a second, then the force it has to exert is over half a ton, or if she weighs 110 pounds, equivalent to 10 Gs, 10 times the acceleration due to gravity. And this part requires no suspension of disbelief. If you tell someone, yeah, they were going 95 miles per hour, we stopped them in half a second with a force of 10 Gs, you'd say, yeah, and their neck broke, right? That part is reasonable. And this is why we have airbags in our automobiles. You're in a car, you're going 60 miles an hour, you hit something, the car stops. You keep moving forward because an object in motion remains in motion until acted upon by an outside force. That outside force is coming up in a minute. It used to be supplied by either the steering column or the windshield. They're very rigid, very hard, the time is very short, the force is very large. See, your collision is governed by this equation, and this side is fixed. You're going 60 miles an hour, you're going to come to rest because you hit something. You don't want that to happen, you shouldn't have hit something. Your mass doesn't change. That's the best case scenario. That's what we're shooting for. Okay? So, this part is determined by the collision. All you can really do is affect the time. Airbags do two things. They spread the force over a larger area, so the pressure, force per area, is reduced, and they deform under contact. They give a little bit, as opposed to a steering column, which is very rigid. So that the time of slowing you down might go all the way from 1 millisecond to 3 milliseconds. Doesn't sound like much. But a factor of 3 increase in the time is a factor of 3 reduction in the force. And you go from a force that will knock you unconscious to one that was lethal. And so sadly, the same physics that saves our lives in automobiles was responsible for the death of Spider-Man's girlfriend. I wrote this up in a letter to Wizard Magazine. They published the letter. They said, see, physics shows we were right. It was the webbing that killed her. A few years later, in Peter Parker's Spider-Man number 45, the Green Goblin is still taunting Spider-Man over the death of Gwen Stacy, but now he's changed his tune. Now he says that he tried to save poor Gwen. But before I had a chance to reach her, Spider-Man did something incredibly stupid. Despite the speed of her fall, he chose to catch her in that rubber webbing of his. In the next instant, her neck was snapped like a rotten twig. So, it may have taken over 30 years, but at least now the Green Goblin realizes that it wasn't the fall that killed Gwen Stacy, but it was the webbing. I don't know how well I do with my students, the readers of my book, or with you guys here tonight. But if I can teach a homicidal maniac like the Green Goblin about Newton's laws of motion, I'm making a difference. Now, there's other things, not just mechanics, that we can talk about. There's electricity and magnetism, and I usually discuss this in relation to two supervillains, Electro and Magneto. And I'll give you all a moment, and I'll see if you can figure out which one is associated with electricity and which one with magnetism. Give up? Electro is a Spider-Man villain. He was on a high-tension line and struck by lightning, and thus obviously gained the ability to store electric charge and discharge it in the form of lethal lightning bolts at will. Personally, and this is just me, if I gain mastery over one of the fundamental forces of nature, I don't know if these are the clothes I'd wear in public, but I think this is just like one in a series of bad decisions that lead these guys to a life of crime. Now, here's an example. So Spider-Man, now here's where they get it a little bit wrong. Spider-Man is trying to deflect one of the bolts by tossing a metal chair, tossing some ball bearings in the air, and then he tosses a metal chair overhead, and he says, anyone with any knowledge of science knows that anything metal can act like a lightning rod, as this steel chair is doing. Actually, Peter, anyone with any knowledge of science knows that this is true. If the chair were grounded and there was some place for the electricity to go, it's not attracted because it's a good conductor to ground, not just because it's attracted to metal. Water goes from the faucet to the drain because of gravity. It's not attracted to drains. It's not like if you put a drain on the ceiling, the water would go, "There's a drain!" And you go, yeah, but gravity. Forget gravity, there's a drain! And arc up. It doesn't work that way. It gets even worse. Here he's fighting Electro in another story, and he takes the precaution of deliberately grounding himself. He says, "It's a good thing I grounded myself. I'm able to take the full effect of it thanks to the addition of my spider strength." No, spider strength helps, but man, don't promise me, especially the kids in the audience, if you're fighting a villain with electric powers, make sure you're not grounded. Actually, Superman understands this. This is a scene from Action Comics #1, a reprint, not my copy of Action Comics. I have to work for a living. Featuring the first adventure of Superman. Superman wants some information from this guy here. Nobody knows who Superman is at this point. Nobody knows what he can do. And the guy looks at Superman, looks at the way he's dressed, and strangely decides not to cooperate. Superman grabs his foot and starts running along a high-tension line, and the man panics. Stop, we'll be electrocuted. Superman says, "No, we won't. Birds sit on telephone wires, and they aren't electrocuted. Not unless they touch a telephone pole and are grounded." Oops, almost touched that pole. By the way, I see that look in class a lot. Now, Superman is exactly right. You have to provide a pathway. That's the danger of the high-tension lines. You know how to take a glass of water, filled up to the brim, no cap, turn it upside down, keep all the water inside the cup? Do it underwater. No place for the water to go, stays in the cup. You could be at 10,000 volts. Everything else is at 10,000 volts, no problem. If there's one spot at 0 volts, there's a problem. Right? So this is, oh, by the way, who is this guy that Superman's roughing up? Trying to get information from? What dastardly villain is this? No, it's not Lex Luthor. Worse. This is Bob Gear, the slickest lobbyist in Washington. The first people Superman goes after in his first adventures, 1938, height of the economic depression, crooked politicians, Washington lobbyists, sweatshop owners, guys who run unsafe coal mines. Once he's the head, Superman, of a multi-million-dollar licensing and marketing enterprise, he starts fighting people who want to take over the galaxy but will leave the American corporate power structure safely undisturbed. There's a whole different talk. But here's an example of them in the same issue where they get grounding wrong, they get it right. So here's Electro. He's just got done robbing a bank. We know he's robbing a bank because he's got a canvas bag with a $sign on it. And he runs out and he scampers up the side of the building like Spider-Man. And these two people here say, "Look, that strangely garbed man is racing up the side of the building. He's holding on to the iron beams in the building by means of electric rays, using them like a magnet. Incredible." And again, several things to notice here. One, I'm sure some of the more senior members of the audience share with me the nostalgia for back in the 60s when pedestrians used to routinely narrate events occurring in front of them, providing exposition for anyone who happened to be walking by. Also, why doesn't anyone use the phrase strangely garbed anymore? But also a recognition that this is correct. That electric currents do create magnetic fields. And so this is again an example of a correct use of the superpowers, illustrating correct physics principles. I know electric currents create magnetic fields because I read comic books. Here's an issue of Superboy where he's trying to stop a group of vandals who have broken into an army base, stolen a bunch of tanks, and are joyriding around town. This group of vandals is called the Smash and Grab Gang. I guess because Bloods and Crips were already taken. Superboy says, I'll need that locomotive, a dynamo from the powerhouse, and a few miles of wire. This dynamo will give the current I need when it's hooked up. Now for the windings. A few seconds to wind these miles of wire, and then I've got the biggest electromagnet ever made, and one that can go places. Lucky this railroad runs right through the town. Has anyone been to Fargo? There are my vandals. And then, sure enough, what's happening? We're flying. It's that locomotive. It's a magnet drawing our steel tanks, ignoring the steel in the car. Hey, steel in the building, and anything that's not nailed down. But it's Silver Age magnetism. But we can talk more about magnetism with Magneto, an X-Men villain, the mutant master of magnetism. Here he's polarizing the iron in a rock and tossing it, using it then to attack one of the X-Men, Angel. Here we see him escaping from the X-Men. I can still escape you flying by means of magnetic repulsion. Well, what does magnetic repulsion mean? We have a magnet, and we were used to it being able to pick up things like paper clips, or refrigerators, things that have some iron in them. And that's because these other materials, even if they're not already magnetized, you put them in a magnet and it develops a south pole and a north pole here, and north pole is attracted to south and they're attracted. But not all metals are magnetic. If you try to pick up a gold wedding band or some gold jewelry with a magnet, it won't work. Actually, they are what's called diamagnetic, where it develops not a south pole next to the north, but a north pole. If you can go home and pick up gold jewelry with a refrigerator magnet, somebody's got some explaining to do. Hey, there's candy in here. This process, so gold is called diamagnetic because it develops a magnetic field that opposes the external applied field. Gold is diamagnetic, silver, water. Water is diamagnetic. And since we're mostly water, so are we. And in fact, this is the first step in magnetic resonance imaging. You put a magnetic field on and you polarize the water molecules and the other molecules in your body, and then you ping the level of polarization with radio waves. But so it is conceivable, I suppose, to have a magnetic field large enough that you could levitate an object. I don't know if you could create a magnetic field large enough to levitate a person. But I do know that you can levitate a frog. And that's because if you go on the web and you Google diamagnetic levitating frog, and who hasn't? This is the first video that pops up. And this is a frog, and it's not on the space station. It's actually in the Netherlands, in a magnetic field that's about 200,000 times stronger than the Earth's field, and it's levitating through the diamagnetic levitation, the polarization of the water molecules in the frog. So, here's another example of comic books talking about correct physics. Quantum physics. We can do some advanced stuff. Not just, classical mechanics. Frequently characters deal with parallel dimensions or they're walking through walls. And this part they pretty much get right. Now, I love this guy. Modern quantum theory began in 1925 when Erwin Schrödinger thought of the Schrödinger equation. This is in essence force equals mass times acceleration for electrons. It doesn't look like that, but it is. He does this in the 1920s, he and a small group of other scientists, because they're trying to understand how atoms interact with light. A generation later, the transistor and the laser are invented separately at Bell Labs. You don't accidentally discover a laser. You have to go into the lab and willfully, with malice of forethought, go and build such a device. In the comic books, they're always doing this. They're taking power supplies and printed circuit boards, shaking it, and getting fully functioning death ray. It's not that easy. I've tried. This is in the 50s. A
generation later still, we have CD players, personal computers, cell phones, iPods, DVD players, pretty much everything without which my teenage children would say life is not worth living. None of these are possible without the transistor and or the laser, neither of which are possible without quantum mechanics. If you asked Schrodinger and you said, nice equation, Irwin, what's it good for? You wouldn't say, if you want to store music in a compact digital format, but without really the work of a handful of people, the world we live in would look profoundly different. What is quantum mechanics about? At its heart, the Schrodinger equation says, you tell me the forces acting on an electron, say, and I will turn the crank and I will get this equation, this Greek letter psi, I square it, and it tells me the probability of finding the electron at some point in space and time. And if you have a radioactive isotope, it'll tell me the probability that the isotope may decay, or equivalently I can say, how long do I have to wait before the chance of it decaying is 50%? And that's called the half-life. And it's remarkably accurate. You take 1 million isotopes, and it predicts a half-life of a day. A day later, 500,000 are gone. The only problem is that it can't tell you which 500,000 are going to go until you do the experiment. Physicists hated that. Hated the fact that it only told you probabilities. And so to counter this, they proposed the following thought experiment. They said, say you don't have 1 million isotopes, you've got 1. Let's say it has a half-life of 1 hour, meaning that after an hour, there's a 50-50 chance it either decays or it doesn't decay. If it decays, it'll emit an alpha particle. How do I know that? I'll set it up so that the alpha particle will break open a bottle of poison gas, and the poison gas will kill a cat that I put in a box. It's not what we hate cats, but this way you turn a nuclear event into something macroscopic that's unambiguous. If the isotope decays, the cat dies. If it doesn't, the cat's alive. So you put the cat in the box, you close the lid, you wait an hour. You open up the box. Quantum mechanics says there's a 50-50 chance the isotope does not decay, poison bottle does not break, so we would find a live cat. But there's also a 50-50 chance that we would find a dead cat. No animals were harmed in the making of this PowerPoint slide. Until you open up the box, quantum theory says that the only way to describe the cat is an average of half alive and half dead. That sounds so stupid that we use different language, saying, well, it's an linear superposition of 2 orthogonal quantum states, so when you open up the box, the wave function collapses into either one observable or the other. But basically it's saying it's half alive, half dead. There's been a lot of experiments on this interpretation that seem to support it, involving entangled quantum states. But back in 1957, Hugh Everett III, PhD student at Princeton, proposed an alternative explanation. He says, I'll tell you what happens to the cat in the box. It has nothing to do with it being half alive, half dead. He says, that's what we're saying. He goes, I'll tell you what happens. When you close up the box, you split off 2 parallel universes. And there's no collapsing wave functions at the end of an hour. All you do when you open the box is discover, do you live in the universe where the cat lives or the universe where the cat dies? And for every quantum event for which there's at least 2 different outcomes, there's that many different parallel universes, so that there is, in theory, an infinite number of parallel Earths out there. Needless to say, physicists did not find this helpful. And this has been considered like the crazy aunt of quantum theory up until fairly recently, which is surprising because just 4 years after Everett proposes his theory, experimental evidence supporting it is presented in flash number 123, where the flash from the Silver Age 1960s vibrates over to a parallel Earth and has an adventure with the flash of the 1940s, experimentally verifying Everett's theory and demonstrating that infinite Earths and parallel universes really exist. I say infinite Earths and parallel universes really exist because I read Scientific American, which says infinite Earths and parallel universes really exist. Now, it's not as if we found these parallel Earths, but there is a subset, a small collection of physicists who are taking these ideas seriously. They are called string theorists. And in their attempts to develop a quantum theory of gravity, they have had to dust off Everett's many worlds interpretation and take it seriously. So here's an example of comic books again, being slightly ahead of the curve. I can't not talk to you and tell you about quantum mechanical tunneling. This notion of probabilities leads to something that is very weird. It is no less weird for being true. If you have a metal separated by the vacuum of empty space from another metal, and if you have an electron that doesn't have enough energy to jump the gap and arc into the other metal, quantum mechanics says that there's still a probability that it winds up in the other metal, even though it never jumps over or does anything. This process is called tunneling, and it's not just some quantum mechanical mumbo-jumbo. You've got tunneling diodes in your cell phone. And if this was not a routine, dependable, practically boring phenomena that engineers can design and program and count on, your cell phones wouldn't work. So this is a real thing. You can use this process to actually look at where the atoms are. You can bring a metal tip very close but not touching a surface where it's right above an atom. Some of the electrons can tunnel and be recorded as a current. Where there's no atoms, there's no current. So here, you might recognize this. This is pencil lead, graphite, only real close up. These are carbon atoms. This is a false color indicating the tunneling current. This is from Professor Goldman's lab at Minnesota. Here's a little bit better image showing the hexagonal structure of the carbon atoms on the surface. So you can actually image atoms using this quantum mechanical tunneling process. This device is called a scanning tunneling microscope. You can change the polarity over an atom and pick it up and move it like an arcade game, picking up little, like the monkey with the claw, right? And so here is the Chinese word for atoms written using iron atoms. Each one of these dots is an iron atom on a surface of copper, and we are now getting to the stage where we can design circuits and build things down at the atomic level. And there's going to be all sorts of different and interesting physics that comes into play then. We would like it would be nice if we could have something larger than just an electron tunnel. And if we can ever get something bigger than that tunneling, we'll find that comic books got there first. Here's a scene from the X-Men movie, the movie X-Men from 2000. Here's Kitty Pryde, who we will, is a mutant with superpowers, and we'll see that her superpower actually involves her being able to change her quantum mechanical tunneling probability at will. It's not working. No sound. Let's start again. We were having troubles with the sound before. Man, I hope not. Can you guys hear anything? Physics. Physics. If it works in comic books, it might even be good in the real world. Now, we started a little late because of all the introductions. I want to spend 5 minutes. I don't want to leave you with the impression that absolutely everything in comic books is 100% scientifically accurate. So I want to point out those few cases where they get it wrong, even with a miracle exemption or two. Here is another scene from that movie X-Men. Here is Cyclops, who has the mutant ability to shoot force beams from his eyes, which are kept in check by a special visor that he wears, and presumably his eyelids. And we're going to see what happens when a villain rips his glasses off. We don't actually need the sound for this one too much. Okay. Did you see what was wrong with that from a physics point of view? Let's leave aside the force beams from the eyes. What else was wrong with it? What happened to Newton's third law of motion? If every action has a reaction, then if you're blasting a hole through the roof of Grand Central, your head should be traveling backwards at several hundred miles per hour. Here we see in a training exercise, he knocks a teammate into the wall, and yet his head doesn't snap back in recoil. Obviously, Cyclops has two superpowers: force beams from his eyes and exceptionally strong neck muscles. Here's another thing that the comic books always get wrong. Here's a story from an old World's Finest comic, and here's Superman, and he's carrying an orphanage from one part of town to another. I've read this several times. I still don't know why. He's always doing things like this. He's picking up ocean liners or jet planes or orphanages. Buildings weren't meant to be picked up. Even if it's like this building here, who's not connected to any city water or power. And even if you hold it right under the center of mass, the way he's doing it here, there's still these enormous twisting forces that we call torques that would exceed the structural strength of the building materials, and the whole thing should crumble under its own weight. And you should always be able to tell where Superman's been by the trail of construction material that he leaves behind him. And you should get there, instead of cheering orphans, you should get there holding a few cinder blocks and some piping. And I'll give you something to yell about. But that's not the worst example. It gets even worse. A few issues later, in another issue of World's Finest, and here he is carrying two office towers like pizza pies, and that's not even the weirdest part of this. The weirdest part is what he's saying. I got permission to borrow the two Gotham City buildings you asked for. Who would you ask? Who would you ask? I'll be extra careful. I'll use one hand. It's like, okay. When he first appeared, people fled in terror when he lifted a car overhead. Now it's like, yay, Superman's going to kill us all. But the last example I want to talk about involves a DC Comics superhero, the Atom. He first appeared in Showcase Comics number 34 in 1964. The Atom has the ability to shrink down to subatomic size. And I really mean subatomic. In one story, he and a friend are having a very private conversation as they sit on an electron. And at one point, the friend stops, turns to the Atom, and asks, he says, "We're smaller than oxygen molecules. How are we breathing?" And the Atom gives the only answer he can. He says, "I'm not sure." But I love the Atom. He's one of my favorite superheroes because in his secret identity, he is Ray Palmer, physics professor, who was trying to develop a miniaturization ray, a shrinking ray, and was unsuccessful because it was missing that one key ingredient, which turned out to be a chunk of a white dwarf star. Presumably because it has the word dwarf in its name, it contains shrinking powers unsuspected by astrophysicists. And here we see Ray Palmer lifting up this chunk of white dwarf star, so heavy I can hardly lift it. Puff. I don't know the odds against one white dwarf hitting another out in space. Puff. But it could happen. And when it did, this piece drifted until it landed in this field. White dwarf stars are dense because they're formed of degenerate matter. Puff. Matter from which the electrons have been stripped, greatly compressing them. Well, the electrons are not. They're in there. They're in the lowest quantum states, which make the atoms very rigid. But it is called degenerate matter. He's right there. By the way, in 1964, physics professors drove caddy convertibles. But it is very dense. I mean, very dense. If water has a density of 1 gram per cubic centimeter and lead is 11 grams per cubic centimeter, white dwarf star matter has a density of 3 million grams per cubic centimeter. And so if we assume this rock is a sphere with a radius of 6 inches, we really can understand why Ray Palmer is huffing and puffing. Because that little rock weighs over 50,000 tons. But I have to point out that actually, technically, this is not a blooper. And that is because we physics professors are just that strong. So, one of the positives of all of this media attention was literally hundreds of emails from students and teachers and people long out of college asking if I had written a book. Eventually I wrote a book. It's available for sale. I have one last slide. Please concentrate, focus all your attention on this last slide from the ringmaster of the Circus of Crime. Thank you all very much. And I'm happy to answer questions. Question?
Have you met any of the authors of these comic books, and are they all disgruntled physicists?
The question is, have I met any of the comic book authors, and are they all disgruntled physicists? No, they're quite gruntled. I have actually. And they are very supportive. Some of them have emailed me and with questions that I've answered and that have shown up in storylines. And I get a little credit line in the comic book, so I have to update my CV. They've actually made me like characters sometimes in stories. And, you know, a very well-known comic book author and also novelist, Neil Gaiman, I had a conversation with, and he said that where in the 70s he got excited and enjoyed reading Analog magazine, a science fiction magazine, now he gets that same excitement from reading New Scientist. And that many of them look at what's going on in popular science magazines and New York Times and things like that, and they use this as plot points to jump off on. So there's a lot of interest in this, and they try to incorporate it in the stories, and anything I can do to help, I love it. Yes?
Were you a comic book collector and fan as a child?
The question was I a comic book fan as a child? Madam, what are you suggesting? Yes, indeed. I actually have a very strong memory of reading comics before I could read. Looking at the storylines. As did most of my peers, I gave up the comic book collecting in high school upon discovering girls. A discovery I'm not given enough credit for in the scientific literature, but that's another point I'm going to take up with the National Academy. And then in grad school, I came across them and kind of picked them up again, initially as a way of just dealing with stress during my dissertation, working on my dissertation, and I just kind of stuck with it. And I enjoy it, and I don't really care. I don't view it as a guilty pleasure, because I don't believe in guilty pleasures. You like what you like, and there's no reason to feel guilty about it, unless you golf. Yes, sir?
Have the stories gotten more scientifically accurate over time?
The question is, have the stories become more scientifically accurate over time? Yes and no. A lot of it will depend on the individual writer and artist in some cases as to whether they're following what's going on. Really, a lot of the examples I have come from a few writers at DC Comics who were like science fiends, and they would try to get real science into the stories. In some cases, just as plot points or just excuses to get the story moving. But there was also a real respect for science that came through. And that was also true in the Marvel comics as well. That whenever they thought about the utopian future of this in society in the future, it was going to be one that was based on science. And when you go to comic book conventions, it's striking how many people there are either in high tech or IT fields. When you think about it, comic books really gave object lessons for future scientists. It's important to know the laws of nature, and important to know the rules of the game. Creative problem solving, and a dashing fashion sense. Yes?
Did you notice, I noticed you skipped Wonder Woman.
Ah.
She's involved in Alaska now?
The real Wonder Woman, I don't mess with. Again, one of the differences is I'm not trying to take different characters and explain them. I use characters to illustrate different physics principles. But you can talk about Wonder Woman. You could talk about the pressure on the bracelets as she's deflecting bullets, and it comes up to about 70,000 pounds per square inch, which is why I don't mess with her. She's fighting for our rights in her satin tights. And I'm going to leave it at that. There was another question.
Yeah, you didn't mention Buck Rogers, but the author was awfully creative.
Yes. Buck Rogers. The question was about Buck Rogers. That's exactly right. Buck Rogers was a science fiction pulp story originally, published in Amazing Stories in 1928, August 1928. I just had to look this up. I'm not like that nerdy. Actually, it's kind of interesting that Buck Rogers, in his very first appearance on the cover of Amazing Stories, is shown levitating with some sort of personal jetpack that he has. He had ray guns. There were all sorts of things that, we were expected that in the future we would all be living in Mr. Rogers' neighborhood, and that we would be having these adventures. Here it is, well past the year 2000. Where's my jetpack? Where's my flying car? What we got instead were cell phones and laptop computers. Back in the 30s and the 40s and the 50s, they were really expecting a revolution in energy, when what we got was a revolution in information. And a lot of that made possible by quantum mechanics, which was created around the same time Buck Rogers is appearing. That's why I looked it up. So just in the mid-1920s, quantum mechanics is being developed at the same time people are imagining what the future is going to look like, and the scientists are creating a future that looks nothing, that is way beyond the wildest imaginations. MRI, magnetic resonance imaging, looking inside people's bodies while they're alive, unharmed, in real time. If you saw that in a pulp science fiction story in the 1950s and said that this would be commonplace by 2000, you'd say, yeah, right. You'd never buy a cell phone that had the capabilities of a Star Trek communicator. Where's the camera? Where's the Wi-Fi? I can't store my songs on here, too? All I can do is talk to Scotty? So, in many cases, reality is far outstripped what they suggest. But there's a lot of people I didn't talk about. Way in the back. Yes?
Can you explain in the movie Iron Man what that little energy generator was that you had going?
It was freaking cool, is what it was. That's actually Iron Man's miracle exemption. Everything else in the suit is technologically feasible. Jet boots, oh yeah, we could do that. The exoskeleton, the external armor, that's all fine. Army's working on this. The problem is that the guys have this giant power cord trailing behind them because it takes a lot of power to get that strength amplification like he has. The arc reactor is some technobabble that just waves his hands and says, this is the energy supply, don't worry about it. One thing that is in the Iron Man comics that they didn't really dwell on, but is apparently present in the movie, is how he controls all of this stuff. You never see him press a button or pull a trigger or send a command to activate the boots or the repulsor ray in the palm. In the comics, it's explained that he controls this through a cybernetic helmet. One of my colleagues at Minnesota, Professor Bin He in the Department of Biomedical Engineering, is developing a cybernetic helmet that picks up the EEG patterns of students looking at a computer screen, and they think about moving the cursor to the left or the right, and the cursor moves to the left or the right. They can control something on the computer screen by thinking about which way they want it to move. Playing a computer game, in essence, without a joystick or a pad. Obviously, he's not trying to develop a next generation of computer games. He's trying to develop treatments for people who are paralyzed or the next generation of prosthetics. But back in the 60s, when I was reading Iron Man comics, and you said in 2008 which aspect was the closest to being real, the last thing I would have said was the cybernetic helmet. So here again is an example of things that in the comic book that we're now finally catching up to. And it's usually the stuff that you won't expect. Yes, sir?
Does some of the armament now used by the Army and in warfare come from perhaps some of the comic books that the generals might read or something?
No, you're confusing the war plans.
Could you define the word physics for me in the simplest terms?
Physics?
Physics.
Physics is the study of matter and energy. Okay? Frequently thrown in non-living, though I talk to neuroscientists and stuff, so I take it even more broader. So that means there are basic physics principles that no matter what DNA you have or anything else, you're going to be governed by the laws of nature. You're going to be governed by the constraints that we live on a planet with such and such an atmosphere, so much gravity, and so on. And these will determine the beauty of physics. It's not about knowing, having an encyclopedic knowledge of equations and formulas, being able to do calculations like Mr. Spock with robotic speed. It's about asking the right questions. Asking the right questions of the universe. And if you ask them right, you either see what the answer is or how to go about getting the answer. And an example I give in the book, and I frequently do with my students, is I toss a ball across the room, and I say, what questions can we ask? And they say, how high did it go? How far did it go? How fast did it go? The time in the air. And I think there's one question you can ask of tossing that ball that encompasses all of those questions and more. Did the ball have any choice? Did it have any choice? If the ball did not have choice, if it lacked free will, then its path was completely determined by forces external to it. If we can determine what those forces are and see how it affects the motion, then the next time I toss the ball, it will take exactly the same pathway, because it has no choice. I can calculate its trajectory, and it will follow it. It has no choice. And so that is the basis by which we can design airplanes, that we can travel from Chicago to St. Louis, that we have enjoyed the lifestyle that we have today, that we don't have to cower from the lightning. We're not as strong as a bear. We're not as fast as the cheetah. We can't fly like an eagle. We're not as indestructible as the cockroach. Our only ability is our intelligence. It's our superpower. And if superheroes and comic books can inspire some people to learn more real science and do right, it wouldn't be the first time these guys have saved the day.